at equilibrium, the rates of forward and reverse reactions are equal, but the concentrations are not necessarily equal. At the end of the video, he said, well, how many people do you expect to be in each of the groups? Half and half? Well, not necessarily. It could be anything. It depends on the exact reaction. How can we know about the concentrations of the reactants and products at equilibrium? We use something called the equilibrium constant to quantify the relative concentrations at equilibrium. So the equilibrium constant is given the symbol capital K with a subscript EQ for equilibrium. Let's look at a generic chemical reaction. A plus B is in equilibrium with C and D. And here in the lowercase letters, that's the subscript, not the subscript, the coefficient for A. So A molecules of A react with B molecules of B to form C molecules of C and D molecules of D. The equilibrium constant is defined as the ratio of the concentrations of the products raised to their stoichiometric coefficients divided by the concentrations of the reactants raised to their stoichiometric coefficients. This is one of those situations where saying it out in words is not all that helpful. It's going to look like this. So the equilibrium constant equals the concentration of C raised to the power of whatever its coefficient is. If it's a 1, that's to the first power. If this lowercase c is a 2, then this is squared. And that's multiplied by the other product, its concentration, raised to a power equal to its coefficient. And then we divide that by the reactants. So it's the products divided by the reactants. So when we put the bars around it, the brackets, that means concentration of D, and the unit is moles per liter. And so we'll encounter moles per liter a little bit in this chapter. We haven't covered it yet. It'll be okay. We're going to come back to that, I think, in chapter 12. So this is how we calculate the equilibrium constant. So we need to learn how to write an equilibrium expression for a given reaction. So if this is our reaction and we need to write an expression to calculate KEQ, we're going to take the product, NO2, the concentration of that. There's a 4 for the coefficient. So that concentration is raised to the 4th power. Oxygen has an implied coefficient of 1, and so we take its concentration to the 1st power. You could write it if you want to, but it's not necessary. And so those are the products, and then we're going to divide by the reactant concentration, N2O5, to the 2nd power because it has a coefficient of 2. So the coefficients from the chemical equation become exponents in the equilibrium expression. Let's do another one. Write an equilibrium expression for this chemical reaction. So KEQ, we want the products divided by the reactants. So this is the product, HF, and I'm going to put it in brackets, which means the concentration of that. And does it have a coefficient in the equation? It does. So I need to put that 2 as the power on that. So it's raised to the 2nd power. And then I'm going to divide by the reactant concentrations, H2. What's the coefficient in the equation for H2? It's an unwritten 1. So then the power for this concentration is an unwritten 1. The other reactant is F2. It also has a coefficient of 1, and so its power is 1. And that's the equilibrium expression for that chemical reaction. Well, what does KEQ mean? If KEQ is very large, that tells us that the forward reaction is favored. There's going to be a lot of product and not much reactant at equilibrium. And when we mean large, we mean large. So this reaction between hydrogen and bromine is in equilibrium with hydrogen bromide. The equilibrium constant is 1.9 times 10 to the 19th. That's a really big number. At equilibrium, there's a lot of HBr and there's very little of the reactants left. If KEQ is small, that tells us that the reverse reaction is favored and there's going to be more reactants than products at equilibrium. This equilibrium constant is 4.1 times 10 to the minus 31. That's a mind-bogglingly small number. This small KEQ tells us that this goes in the forward direction only a little teeny tiny bit. At equilibrium, there's going to be almost no product. It's mostly going to be reactant. So, large equilibrium constant, here's the reaction. What we observe at equilibrium is that it's almost all product. There's very little reactant. This is the equilibrium expression. It's the concentration of the product, HBr, squared, divided by the concentration of hydrogen and the concentration of bromine. If this is a large number, that means that the concentration of the product is big and the concentration of the reactants is small. Small equilibrium constant is the opposite. In this reaction of nitrogen and oxygen to form NO, at equilibrium what we'll see is there's very little NO in this box. It's mostly reactants. The forward reaction doesn't go very far. It's very slow. The reverse reaction is favored, and so we mostly have reactants. This is the equilibrium constant for this reaction, the equilibrium expression. If this is a small number, then the numbers on the top in the numerator have to be small, and the numbers in the denominator have to be big. The concentrations of reactants is large compared to the concentrations of product. So this is a summary of those ideas. If KEQ is much smaller than 1, the reverse reaction is favored. The forward reaction just doesn't go very far. It makes a little tiny bit of product. It just doesn't go very far. It's in equilibrium, and so the product that is being made is also reacting to form the reactants. But when you look at the concentrations, the concentration of product is very small. If KEQ is much larger than 1, the forward reaction is favored. And it proceeds virtually to completion. There's very little reactant at the end. When KEQ is about 1, and here when we say about 1, that's, like 0.1 to 10 would be considered about 1, because these things are extremes, like 10 to the 19 and 10 to the minus 31. In this situation, neither direction is favored. They both proceed fairly equally, and you're going to have a significant amount of reactants and products present at equilibrium. So you'll have both present.